Welcome to another data science deep dive on our technical track. In the following presentation, Nikunj Aggarwal, staff software engineer at Citizen, talks about how Citizen scans thousands of public first responder radio frequencies 24 hours a day in major cities across the US to provide real-time safety alerts about incidents like fires, car collisions, and missing persons. Enjoy.
Hello, I'm Nikunj from Citizen. Today I'll talk about a crazy journey to open up the 911 system using a convolutional neural network. So the mission of Citizen is to make your world a safer place. To that effect, we scan thousands of first responder radio frequencies 24 hours a day in most major markets across the US. Based on the audio, our operations team alert people about major incidents like fire, robberies, missing persons, and all this happens in real time so that you can take the required actions. Our software-defined radios capture large swaths of radio frequencies, which are then sent to our operators. Only a small fraction of audio is actually useful and is used in creating incidents. Listening to all the police dispatch calls is very unscalable. So we generate about 1,000 hours of audio every day. And if you were to listen to everything, we would need more than 100 operations staff working in multiple shifts all day. So we started exploring a machine learning solution to scale our operations. Here's a diagram of how the system works. Our software-defined radios are placed in every major US city. They tap into police dispatch radios and upload the audio to our API servers. From the API servers, they are stored in our SQL database and then eventually sent to our operators. The operators find the relevant clips and then create incidents, which are then sent to our notification engine. Our notification engine then notifies users who are near those incidents so that they can take precaution. So to scale our operations, we started off by training a binary classifier using transcriptions as input. Firstly, we picked a public speech-to-text engine with the lowest word error rate on our data set. Then we tuned the speech-to-text engine through custom vocabulary and boosting words. So boosting is a feature in some of the speech-to-text engines which let you prioritize uncommon words. For example, assault is an uncommon word for most of the speech-to-text engines as they're trained on data sets like Wikipedia. So without boosting, we noticed that a bunch of speech-to-text engines were transcribing the audio as assault instead of assault. So we had to use boosting to counter that. Finally, we trained a binary classifier using mainly the transcription as features, and then we added more features such as the radio channel, alert tones, and past incidents. So as the diagram shows, the audio comes to our worker nodes. We extract things like alert tones, frequencies, and also send the audio to a third-party transcription service to get the transcriptions. Finally, all these features are fed into an XGBoost classifier, which emits a confidence around whether the clip was useful. We also played around with the address detector on transcriptions so that the operations can be made even more efficient. Once the classifier achieved the desired precision recall, we decided to launch the model in one city. So in that city, operations only listened to flag clips and created incidents. This reduced the audio volume to be listened to by at least 50% and without any major change in incident recall. So this single city launch showed that operations can be made efficient without major degradation in performance in those cities. This was actually a very promising outcome for us. So the diagram is from our actual UI, which shows how initially operations went from listening to all clips every time to slowly seeing what clips the model would have flagged and getting confidence in the model, and then finally only listening to flag clips. Once this model was in production for a single city, we found bottlenecks in the system. So the system was heavily reliant on transcription accuracy, and the speech-to-text engines are trained on phone audio which is acoustically very different than radios. As a result, the transcription accuracies varied a lot, especially when channels were noisy or had special alert tones, which are unique to police dispatch systems. The major variations were in different systems used by different cities across the US. This system was completely unusable for older analog systems as they were a lot noisier. So New York City is our biggest market as we have millions of users there, and also the highest audio volume because the crime rate in New York is very high. Since New York had an old analog system, a model couldn't be used, and why that vastly reduced the efficacy of the model to optimize the operations, since we had a lot of operations folks covering New York. To fix the performance bottleneck on transcriptions, one option we considered was to train a custom speech-to-text engine on our own dataset. Some of the advantages of that system was that the model, since it was custom for our vocabulary and acoustic profile, it was theoretically supposed to be superior to an off-the-shelf model. Some disadvantages, obviously, were that training a speech-to-text engine from scratch is not easy. You need at least 100 hours of data for a very limited vocabulary. And if you were to actually train for the full vocabulary, you need thousands of hours of data. Moreover, models such as deep speech were very slow to converge sometimes, needing days, if not weeks, and they require a lot of hardware. So even though this option could have been the most performant, it just didn't fit our timelines and available resources. As a lean startup, we wanted to emphasize on a solution which can be trained quickly and needs limited data. Since we only need to know the presence of keywords and there were no long-range dependencies between audio segments, we could use a computationally simple CNN, or a convolutional neural network. So since CNN is simpler than RNN, LSTM, or a transformer, and it theoretically could have worked for this case, we had a bias to try that out first. Here's our network architecture. And to be honest, a lot of this came from hyperparameter tuning, since it's very hard initially to figure out what layers to use and in what order. So we noticed our audio had a lot of white noise across channels. So we added Gaussian noise filter for robustness to channel noise. We also added a batch normalization layer to help with model convergence. We added max pooling 1D layers to handle minor variations in speech across speakers. Then we had a bunch of Con 1D layers, which was our convolutional kernel. We also tried a bunch of other layers, for example, dropouts, and then rejected those because they just didn't improve the model performance. We actually also briefly tried out RNNs, LSTM, and transformer, but on a small data set. But the training was just too slow, while the performance difference wasn't commensurate with the added complexity. So we just favored going down the path of CNNs further, since they were working fine for us. To start training the model, we split the audio into fixed duration subclips. For each subclip, we converted that into Mel frequency septal coefficients, along with the first and second order derivatives. We outputted 1 if any keyword was present in the subclip. So we noticed that long subclips made it harder for the model to figure out what in the subclip was useful and affected model convergence. Whereas if the subclip duration was really short, then it was very likely that a word will be spread across multiple subclips, and that will affect the performance of the model. Hyperparameter tuning vastly helped here too, to decide the subclip duration. We also tried a bunch of other representations of audio other than MFCCs, as mentioned in the literature, but they did not make a measurable difference. And since MFCCs were much more commonly available, we stick to those. To generate training data, we leverage human annotators. They annotated words from our vocabulary along with their start and end positions. As shown in the figure, annotators can listen to waveforms in our UI, zoom in and out quickly, Finally, once they found a word which is present in our vocabulary, they can just drag and drop from the UI and type out the word. And this eventually stored the word and the start and end positions in a CA sweep, and they were done. So this heavily optimized their workflows. We also added about a 10% overlap in clips given to annotators so that we could compare how different annotators were performing. And using that, we were able to get the precision recall for the data generation process. Once we had that, we used this information to further train our annotators and make them more consistent over time. Once we had a base model, we started tuning it to improve the precision recall. We quickly noticed that the model actually got really good at detecting words which were common in a data set. For example, fire is extremely common. But the model started struggling on rarer words. For example, machete probably occurred twice in our data set, and the model was not very good at detecting that. We tried a few approaches to make the model better at rare words. For example, audio clips usually have gaps where nobody's speaking. So one approach which seemed very promising was to take a rare word from one audio clip and insert that into gaps in other audio clips. Although this sounded really good theoretically, it only marginally helped improve the performance. Similarly, we also tried adding random noise to audio clip or rare words so that we can increase the number of samples. But even that did not help a lot. The major boost throughout our training process we saw was usually to get more training data for the words. However, since our labeling process was looking at all audio clips, we were just constantly creating more and more samples for the common words, whereas the rare words were getting left out. To fix that imbalance, we used a partially trained model, which was already very good at common words, and used that to filter out clips where it was very confident that common words are present. So this ensured that the annotators were not just focusing on the common words, and other words were also getting noticed. Many parameters for the model, as I mentioned earlier, were decided based on hyperparameter tuning. For example, layer architecture for neural network was heavily decided by hyperparameter tuning. Similarly, subclip durations, as I alluded to earlier, was through hyperparameter tuning. We even figured a good combination of when do you get more data and how much synthetic data to create through our tuning. And finally, we had to figure out the minimum sample needed for vocabulary word, and that also came through tuning. Eventually, the model was good enough for launch. We started off with A/B testing the operations workflow in some boroughs of New York City. We saw no measurable degradation in incident quality when operators used flagged-only clips by the model versus everything in the system. And since we only flagged a small fraction of clips, the audio volume for operations was cut down by 50 to 75%. Somewhat surprisingly, the model transferred well to other analog cities, for example, Chicago, even though they had a very different dispatch system. This was a great validation for us since we didn't have to redo the whole process of getting more than 100 hours of audio for every city. Overall, this helped us provide a generic solution for radios which could work even in noisy analog conditions. In conclusion, our deep neural network was broadly applicable to police audio from major US cities. Picking computationally simple CNN architecture over RNN, LSTM, or transformers helped us to be a lot more aggressive about hyperparameter tuning. Simplifying our labeling process helped us quickly get an initial data set and begin our training iterations. Starting with the publicly available speech-to-text engine and showing non-trivial gains in operations helped us gain the buy-in to actually invest more into a neural network from scratch for a problem. Even though the initial model based on speech-to-text engine was only applicable to a small number of cities with great quality audio, we got a lot of learnings about the operations workflow, and they also got comfortable with addition to machine intelligence in their workflow. And this helped us out a lot in our later efforts. If we had started off with a year-long project of just writing a neural network for classifying audio, we may not have gotten far without doing this exercise. Finally, this model is now being used to launch Citizen to every new city across the United States, and we've quickly grown our presence to more than 20 cities as a result. That's all I had. Thank you for listening. I hope you found the talk useful. We have a few minutes for questions, and I'd be happy to answer any you may have.
That was Nikunj Aggarwal, staff software engineer at Citizen, with his presentation on how Citizen created an end-to-end safety alert system from scratch using a novel application of convolutional neural networks. If you'd like to watch more videos like this, you can subscribe to the DS Insider program, where you will find the comment to do that in the comment section. There you will have access to a lot of on-demand videos just like this one, and you could watch them on your own time. Thanks and enjoy!